All right. Mock exam four. I think you guys went over this in class today, but uh, yeah. Sorry if you're my roommate. All right. Which of the following have the same number of valence electrons? So for this problem, you want to look at which combination of these elements, these trios of elements, are in the same column. Because right, if we look down a column, they kind of all, I guess they all form the same ions if you're in the same column. Okay, so if you look at this first one, boron, silicon, and astatine, arsenic. All right, so boron and silicon and arsenic are in the diagonal on the metalloids, so they're not in the same column. So it's not that one. Iron, ruthenium, and osmium. Um, so for this one, these are all three transition metals, so you can't really compare them on the number of valence electrons because each one of them will have, I guess, they'll form different ions, so they'll have different number of valence electrons. So not that one. Calcium, potassium, and scandium. Um, is that scandium? I think so. But these are also not in the same column, so it cannot be that one. And then we have nitrogen, phosphorus, and arsenic. These are all in the same column. They're all in that in the row 15 or 5A. So these all have the same number of valence electrons. Which of the following represents the Lewis structure for the anion N3 minus? So nitrogen, like we just saw on this on the first problem, is in row 15. It's just nitrogen, phosphorus, like it's like this. So these will all form 3 minus ions to complete their octet. Um, so yeah, they'll have a full octet. So we can do this 8, and then remember that if we have an ion, we need to have brackets and then the electrical charge on the outside. So that one is C. Can't be this one because this doesn't have a full octet. This just has nothing. That's as if it formed um, a cation, which it doesn't do that. This just looks funky, and this doesn't have the brackets. All right, which of the following elements can have an expanded octet? So remember the rule for this is just that any elements in the third row or the third period and below can have expanded octets. So selenium is in the fourth row. I mean that's automatically the answer, or is it? We can look at sulfur. That's in the third row. Uh, bromine is in the fourth row. Phosphorus is in the third row. So it's actually all of the um, all of the above. The condensed electron configuration of selenium, element 34, is, so remember for noble gas notation, you just go back. I guess you start with the noble gas core, which if we see selenium is 34, so that's in the fourth row. The last complete row ends at argon, so we start at argon, and then we start at 4s2, and then we cross the transition metals, so then we go down in energy levels to 3d10, 5 orbitals, 2 electrons each, and then we go back to 4 for the p orbitals, and then it goes starting at 31 in 4p. It's gallium, germanium, arsenic, and then selenium. So it's 4p4, and then that answer is going to be answer choice D. Which of the following statements are false for carbon dioxide? Um, it looks like this is going to want us to draw a Lewis structure to talk about polarity. So we should do that. So we have C, O, O, and we know that there are a total of 16 valence electrons, right? 6 from each of the oxygens and then 4 from the carbon. So if we have 16 to go around, so we've already used 4 here. Let's just throw in double bonds and see what that does. 1, 2, 3, 4, 5, 6, 7, 8. And then we've got 2, 4, 6, 8, 10, 12, 14, 16. And well, that's the Lewis structure for carbon dioxide. And we can see that there's no bond dipoles, there's no polarity or anything. So then we can look at the answer choices. And let me go back. There are like bond dipoles, but they're equally canceled out on both sides because it's the same element, the same electronegativity difference on both sides. So then we're looking for the false statement. The oxygen atoms would have a partial negative charge, and that is true because oxygen is more electronegative than carbon, so that is true. The carbon would have a partial positive charge. That is true because it is the least electronegative part. Um, each individual CO bond is polar with the dipole moment pointing towards the oxygen. Um, that is true, so that isn't false. And then this molecule is polar, and like we just showed, or like we have just showed, we drew the Lewis structure, and the dipoles cancel out in this linear fashion. So the overall molecule is not polar. So this is the false statement. Oh, and there's also an all of the above, but that's not true. How many core electrons are in calcium? So we see that calcium is on the fourth row of the periodic table. So we just need to consider every electron before the fourth row, because those are all completely filled. And then we can kind of look at this by drawing the noble gas notation for calcium. It's just going to be argon core and then a 4s2. And then we see that argon has 18 valence electrons, or has 18 electrons total, which is, this is the core part. So the answer is 18. Choose the bond below that is most polar. You can draw these one out. I guess it doesn't really help you, but you just need to be aware of um, of the trends for electronegativity, and that kind of dictates how polar a bond is. So the larger the electronegativity difference, the more polar. So we see that FF, that is going to be a perfectly covalent bond. There's no polarity, perfectly nonpolar. And then we have, and then we're comparing the noble gases and everything in that seventh row. So I guess if we draw the row out, we'll have F, Cl, Br, iodine, and then astatine. So remember the trend for electronegativity is it decreases down and it also decreases to the left, right? So that means this is going to be the least electronegative, and then F is the same in all of these, which is the most electronegative element. So then the biggest difference would be between fluorine and astatine, which makes the bond the most polar, so that's E. Predict the electron geometry of aluminum bromide, tribromide. I don't know what that is. But we see that there are a total of 21 valence from this and then 3 from this. So 24 valence total. And I'm sure you guys have probably picked up on some trends. Each bond or each bonded element is just going to have 8 from the single bond in all of its lone pairs. So you can just kind of look at that. It's 8 for each of the bonds in the lone pairs connected. And we know that aluminum is one of those elements that can have a decreased octet or I forgot the term for it, but a smaller octet than 8. So then we know that with only 3 bonds and no lone pairs, this is going to be trigonal planar. Give the characteristic bond angle for a molecule with the trigonal bipyramidal shape. So if we remember that the trigonal bipyramidal shape is going to be something like this. Again, I guess I should probably draw this like that, and then we know that around these molecules it's going to be 120, and then from the axial molecules to the equatorial molecules is going to be 90 degrees. So then the answer is 90 and 120. What is true about a CC double bond as compared to a CC double bond? So we know that double bonds are stronger, so we can automatically rule any ones that say regardless of, or that say the opposite of that. So the CC bond is weaker, so we can cross out these ones where it says it's stronger. And then we also know that because CC bonds are stronger, that means that they're holding the two molecules or the two atoms in that bond stronger. So that's going to be a shorter bond. So then the answer is going to be D. Whoa. I did that wrong. We were talking about a double bond just then. the answer is going to be A, right? Because the CC bond is going to be weaker, so it's not going to hold those atoms in the bond as tightly, so the bond will be longer. Yeah. What orbitals does the n equals 2 shell have? This one's kind of just like memorization, and also like with the quantum numbers. I think, yeah. So if n is equal to 2, for L, the quantum numbers for the orientation, or like what types of orbitals you can have, is going to be 0 to n minus 1. I don't know if we actually went over this in class, but then if n is equal to 1, this goes from 0 to 1, so you can have either a 0 type orbital or a 1, which is just the S and P. And then that's going to be the answer of B. Okay. In the Lewis structure for nitrate that is shown below, give the formal charge on the nitrogen atom. So for formal charges, this is what we use to, to tell which best resonant structure is the most likely to occur in nature. And then we remember that resonance, or that the formal charges are just is equal to dots minus lines. I guess we have to include valence minus dots minus lines. So we see that nitrogen has 5 valence electrons minus 0 dots minus 4 lines connected to it is equal to plus 1 for the formal charge, which is answer choice D. Choose the best Lewis structure for OCS. Okay. So oxygen has 6 valence, carbon has 4, sulfur also has 6, so that's equal to 16 total valence. 1, 2, 3, 4, 5, 6, 8. Okay, so I think all of these actually have like proper amounts of valence electrons. So for this question, we just need to evaluate formal charges, and we remember that for ions, the formal charges, or the sum of all of the formal charges must equal the charge on that ion, and then for neutral atoms, all the formal charges must equal to 0. And then if there are any formal charges, we want them to be on the more electronegative elements, right? Because we want those to have more electrons because they're more likely to hold on to those. That's what electronegativity is. So then if we count formal charges, let's start with the first one. So carbon has 4 valence electrons, and there's 4 dots connected, so the formal charge is just equal to 0 for carbon. And sulfur has 6 valence electrons, and then has 2 dots and 4 lines, so it's 0. And then we see for oxygen, it also has 6 valence electrons, and it has 4 electrons, 4 dots, and then 2 lines connected to it, so it's also 0. So then we can pretty much almost conclude that the answer is going to be A, but we can check the other ones just to do so. So the formal charge on oxygen on this one is going to be 2 dots, 3 lines. It's going to be 6 minus 5, which is plus 1. This one's going to be 0 for 4 lines. And then this is 6 minus 7, which is negative 1, which the sum of the formal charges does equal, it does equal 0, like it should, because it's a neutral atom, or neutral molecule. But remember, like the rule, like we just said, that we want everything to be 0 or close to that as possible. And like we just saw on the one above, the orientation in the setup of the Lewis structure can be done with 0 everywhere. All right, and then we can continue this. It's the same thing on this side. We have minus 1 and then 0 and then plus 1, which isn't as optimal. This one has this one just doesn't even have that has more valence electrons than we have to play with, so it can't be that one. And then this one has 1, 2, 3, 4, 5, 6, 7, 8. 8 times 2 is 16, so this does have the correct amount. And then the formal charge on this left oxygen is going to be plus 1, right? Because 6 minus 2 dots minus 3 lines. Same thing for this over here. And then the formal charge on this carbon is going to be 4 minus 6 lines, so it's going to be -2, which does equal 0, but that's an even worse orientation than B and C, so it can't be that. So like we saw at the beginning, the answer choice is A. Place the following in order of increasing radius. For this one, you just want to remember, I guess, the trends of atomic radius. So atomic radius will, I guess, decrease over here. And also decrease going up. And you can do the same thing with increase. It increases to the left and increases downward. So we want to place these in the order of increasing atomic radius. So smallest first. All right. So we see oxygen. That is going to be fairly like over here. And then we have tellurium, which is about over here. And then we have fluorine, which is right here. It's more so over here, but yeah, it's right there, kind of. Oops. All right. So if we know the trend that the smallest is going to be at the top right, yeah, the smallest is going to be kind of over here. We know that fluorine is going to be smallest, so that automatically crosses out A, B, and E. And then we use the trend again. We see oxygen is right next to fluorine, so that must be the next smallest element. And then we can cross out D, which is the only other answer choice. And then answer choice is C, because tellurium is way down there. It's got way more energy levels than oxygen or fluorine. So it's going to be way bigger. Choose the best Lewis structure for I don't know what that is, ASO4 with a 3 minus charge. In this, just like this problem over here, this 13, we want to use formal charges to evaluate this, and we know that the sum of formal charges must equal to the charge on the ion. And then if we, like in this case, if we are going to have formal charges, we want the formal charges to be on the most electronegative atoms, which in this case, oxygen is way more electronegative than arsenic. So I guess we can just start by counting this. So on this answer choice A, on every single one of the oxygens, there are 6 dots and 1 line, so that's going to be -1, -1, -1, -1. And then this arsenic is going to be, there's 5 valence electrons and only 4, so it's going to have a +1. One of these +1s is going to cancel, leaving a +3. That's an okay Lewis structure, but like we said, if we want charges, we want them all to be on the oxygens, on the more electronegative elements. And if we do the same for this, we have a 0, 0, -1, 0, and then a 1, 2, 3, 4, 5, 6, 7, 8, 9, a 5 minus 9, a -4. That doesn't make any sense. Yeah, this answer choice C is just wrong. I think it has more electrons used than we actually have available. Okay, and then we can go back down to this. On every single one of these, just like the first problem, or on the A answer choice, we have -1s everywhere. And then on the arsenic in the middle, we have 1, 2, 3, 4, 5, 6. So that's a -1. Yeah, those formal charges don't even add up to -3, so it can't be that one either. If we look at answer choice B, we have -1, -1, -1, right? Because we just did 6 minus 6 minus 1 for dots and lines. And then for this one, we have 1, 2, 3, 4, 5, 6. We have a 0 formal charge, and then we have a 0 formal charge. This is a contender for the best Lewis structure, because like we said, we got all of the formal charges on the more electronegative atoms, and the charges add up to -3. And then we have one more answer choice to check. So we have, for these two right here, we have 0 and 0, and then we have -1, -1, and then we have -1 here. And I guess against our rationale on answer choice B, the formal charges are on that central atom, which we don't want. So yeah, answer choice is going to be B. Which of the following is the best explanation of why ionization energy increases across a period? So so increases across a period. So going to the right. All right. So this is just like the worksheet we did in class, where we found the electronegative, or I guess the effective nuclear charge on the entire row, starting at sodium, ending in argon. And we saw that argon was going to hold the valence electrons the strongest. And that's kind of the answer to this problem of why the ionization energy increases across a period. So if we know that Z effective has the trend of increasing to the right, right? So when the effective nuclear charge increases going across a period, just like the answer choice says, you can kind of think of this in the terms of Coulomb's equation, or Coulomb's law, is equal to Q1 Q2 over R squared, where you want, I guess, if we can think of this first charge as the nucleus, and then these as the electrons. As the effective increases, as you go across a period, you have more protons in the nucleus. So you have a greater product of both of these charges in the numerator of this Coulomb's equation. So that increases the attraction, the energy between them. So that means things are held more tightly. And that's kind of the answer to the problem that says, let's see what this is. And yeah, the answer is just D, because as effective nuclear charge increases, all of the electrons are held more tightly, the radius gets smaller, so it takes more energy as you go across a period to pull off those electrons. All right, and we kind of almost said this with 16, the answer for 17. The interaction between two charges is the strongest when, and we can think about this again in terms of Coulomb's law. Let's go to K Q1 Q2 over R squared. If we want this value E to be the largest, we want this to be large, this numerator, and then we want this to be very small, just because there's an inverse relationship. Whenever radius gets smaller, the interaction increases. So then looking at our answer choices, we have the magnitude of the charges is small, we don't want that. The magnitude of the charges is small, we don't want that. The magnitude of the charges is large, we do want that. And the distance between the charges is small, we do want that. We can say maybe to that one, and then we have this one on the other page. The magnitude of the charges is large, we want that, and the distance between the charges is large, we do not want that, right? Because energy and radius are inversely proportional. We want radius to be small for energy to be large, so the answer choice is going to be D. Determine the electron geometry and molecular geometry of ICl3. Okay, so we first start by counting the valence electrons, right? We have 21 total for the 3 chlorines, and then another 7 for this iodine. Not total there, so 28 total. We can start with just our skeletal structure, and we'll have iodine in the center because, right, we want the least electronegative atom in the center. Cl, Cl, Cl. You can kind of just start by placing lone pairs and everything and see how many you have left and what you can do with it. So placing lone pairs and the bonds with the chlorines, we have 24 used. So we have 4 left, and the chlorines have already filled their octets, but the iodine can expand its octet because it's in row 5, and that's greater than row 3. So we can just throw these last 2 lone pairs on the iodine. So we have a total of three three bonds and two lone pairs, so that's 5 electron groups. So for 5 electron groups, your electron geometry is going to be trigonal bipyramidal. So we can already cross out 3 of these answer choices. And then we have 2 lone pairs. And I guess we can kind of draw this. We can try to draw it. We have a Cl, and then we have a Cl, and then we have a Cl, and then we have a lone pair over here, and then we have a lone pair coming out of the page. So and then it's kind of a poor drawing, but that's a T shape. So answer choice is B. And if there was only one lone pair, that would be seesaw. Okay. Determine the electron geometry and molecular geometry and polarity of the carbonate ion. So first we can start off with the skeletal structure. We put carbon in the middle because it's the least electronegative. We have 0, 0, 0, not 0, there's oxygen, sorry. And I guess we forgot to count the electrons. So oxygen, 6 times 3, there's 18 total for that, plus 4 for this, plus 2, because we have this minus 2 charge, is equal to 24 total. And then 24 total, just like that last problem, 24 total with 3 atoms bonded is just going to be 3 elements bonded with full lone pairs. But in this case, that doesn't work. Sorry. Because carbon would not have its octet completely filled. And then we can verify that this still works just by just counting electrons. So we've got 8 total for this one, 8 total for this one, 8 total for this one. So that's still 24, and that seems like it still works. And we can even count formal charges to evaluate this further. So on carbon, it's going to be 0. On this oxygen, it's going to be 0. On this oxygen, it's going to be -1. Same for this one, and that adds up to the same value as the charge, which is -2. So we know this works. All right, and then so there are 3 electron groups, right? 3 things, 3 oxygens bonded to this carbon. So we know that is going to be trigonal planar. All right, so we can automatically cross out A and B. And then there are 0 lone pairs. So we know that we can cross out C because that has been in the molecular geometry. If there are 0 lone pairs, is the same as the electron geometry. And then we see that this is trigonal planar with all the same atoms bonded to the central atom. So all the dipoles are going to perfectly cancel, making this a non-polar polyatomic ion. Answer choice E. Consider the molecule below. How many sigma and pi bonds are there in the molecule? This one was pretty easy. You just you count that a single bond is going to be 1 sigma. A double is 1 sigma, 1 pi. And a triple bond is going to be 1 sigma, 2 pi. All right, so then we just count that. So there are, let's just say, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there should be a total of, there's 9 bonds total, so there should be 9 sigma bonds. So we can cross out answer choices A, B, and E. And then we need to look to the double and the triple bonds. And then we see that there is a double bond here, and then a triple bond. So there should be a total of 1 pi from here, 2 pi from here, and then 1 pi from here for a total of 4 pi bonds. And that is our answer choice D. Draw the Lewis structure, or number 21, draw the Lewis structure for XeF2, and what is the hybridization of the Xe atom? Kind of a weird problem where it cut off. We can do the work on this page though. So xenon has 8 valence electrons, fluorine has 14 total, 7 for each, so that's going to be a total of 22 valence electrons. And then we can start off with the skeletal structure. Xe, we can just draw it kind of linear for now because we don't really know what's going to be happening. All right, so then if we fully complete the octets for these fluorines, we'll have used 8 for each of the bonds in lone pairs, making that 16 used, so we only have 22 minus 16 is just equal to 6 electrons left. So then, and we know that xenon is in row 5, so that can expand its octet. So then we can just kind of throw the lone pairs onto the central xenon. All right, and then, so when looking at hybridization, it's really just counting electron groups attached to that atom. So we see that xenon has 3 lone, 2 bonds, which means that there are 5 total electron groups. All right, and then with 5 total electron groups, that means our hybridization is going to be sp3d for a total of 5 characters, if you want to think of this as like S, 3 Ps, and 1 D. And if there were like 4 electron groups, it would be sp3, or if there were 3, it'd be sp2, and if it was 2 electron groups, it'd just be sp, and going greater and less than that, the trend continues. So we know that sp is not the answer. We know this isn't the answer. We know this is an answer. This is probably the answer. This isn't. And the answer choice is D for 5 electron groups attached to the central xenon. Which of the following molecules are polar? Hint to draw Lewis structures. Okay, so we can start with PCl. All right, and we should probably count valence electrons first. So we know that phosphorus has 5, chlorine, or each chlorine has 7, so that's going to be 21 plus 5 is equal to 26. Yeah, so we know we fill these, and we use 28 with all the bonds and lone pairs on each of the chlorines combined is 24. We have 2 more left, so we can just throw a lone pair on phosphorus because that's in row 3, and it can expand its octet. Actually, it needs to be on that. To complete its octet, and we know that for tetrahedral for a tetrahedral electron geometry molecule, if every single one of the electron groups is not the same, then it's going to be polar. So we know that this is polar, and then we can go to SCl2. So we can just draw that first for our skeletal structure, and then we see that sulfur has 6 valence electrons, and then each chlorine is 7 for a total of 14, so that's going to be 20 total. 14 plus 6, yeah, that works. Okay, so then we have, just start with that, I guess. So then once we see that, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 16 used total. So we probably don't want to actually use that orientation. Let's start with adding lone pairs just to everything at first. Okay, so in this orientation we have used 16 so far. We have 4 left, and then we can just add lone pairs onto the sulfur because it's in row 3 and it can expand its octet. Actually, the same thing, it needs to have those to have a full octet. And we know that this is tetrahedral. Again, there's 4 electron groups. And if they're not all the same, then this molecule is polar. So we know that this is polar as well. And then we can have CF4. And remember that in this plus sign shape for tetrahedral doesn't actually mean that it looks like that. It's going to look like the tetrahedron. All right. So we have 4 total valence electrons from carbon, and then we have 4 times 7 is 28. We have 32 total valence electrons for CF4. So if we just fill the octets of all the fluorines, we'll have already used 32. And then if all the molecules are equal, or all the atoms are equal, for tetrahedral electron geometry, we know that this is nonpolar. So then the answer choice would be that 2 of the above are polar. What period 3 element is consistent with the following ionization energies? Okay, should be pretty easy. So we see that the big jump is right here at the 4th ionization energy, which means that typically that the big jump indicates that you've gone up to the next energy level and you're trying to steal from that element's core electrons, which are held way more tightly. So if we look at that, if we see that it takes 3 electrons or 3 ionizations, and then we're finally at the core on this one, we're stealing from the core on this 4th one, we know that there must be 3 valence electrons. So then we just check all of these. So we see that magnesium only has 2 valence, aluminum has 3, silicon has 4, phosphorus has 5, and sulfur has 6. So, I mean, the big jump wouldn't be for any of these until the 5th one or the 6th or the 7th. But we see that for aluminum, B, answer choice B, we see that it has 3 valence electrons, and that corresponds to what we saw, that there's 3 electrons taken away from the valence shell, and then you pull from the core electrons on the 4th ionization. All right, use the bond energies provided to estimate delta H of reaction for the reaction below. All right, these are kind of tedious, but you just need to draw all the Lewis structures for all of these. So we see that N2 has a triple bond with 2 nitrogens, plus 3 times H2 is just a double bond or a single bonded hydrogen to a hydrogen, and then we see that creates 2 moles of NH3, and we've done this this one a lot of times. Let me see. Okay. So we see that we need to break one triple N bond, 3 single H bonds, and then we need to break, so for 1 mole of ammonia, there are 3 NH bonds, but we have 2 moles, so we're breaking a total of 6 NH bonds. And then remember that if you're using bond enthalpies or bond energies to calculate delta H of reaction, you do bonds broken minus bonds formed. So we break these bonds and we form these bonds. So then we do, not delta G, delta H is equal to broken minus formed is equal to, so we have a single triple bonded nitrogen bond. So we do 946 plus, we add up all the bonds broken, and then we have 3 HH bonds, which is 3 times 436, minus the 6 times, or the 6 NH bonds that are formed, which is 389. 389 is equal to all right, got to use a calculator for this one. So we do 946 plus 3 times 436 minus 6 times 389. And then we get an answer of negative 80 kilojoules for the delta H of reaction at standard state conditions. All right, in which transition requires a photon of the shortest wavelength? Okay, so remember this equation that energy is equal to Planck's constant times the frequency, which is equal to h c over lambda. So we know that the relationship between energy and wavelength is inversely proportional. So the greater the wavelength, the smaller the energy, and the smaller the wavelength, the greater the energy. So, and this question is asking for the shortest wavelength. So we know that using this proportionality statement, that the shortest wavelength is going to be the greatest energy, which is going to be the greatest jump from energy levels. So we have answer choices n, or from n is equal to 3 to 4, or 1 to 2, and then 1 to 3. There's only 3 choices. So we see that, and I don't know if you guys remember, like the energy transition things is like going to 1 is here, and then 2 is here, and then 3, and then 4. It gets like really close to each other. See, like 4, 3, 2, 1. So we know that it can't be 3 and 4 because those are really far out, and those are going to be close to each other. It doesn't take much money, or doesn't take much energy to move between those energy levels. And then we have a contender for 1 to 3, or 1 to 2, which is just here. And then our other one is 1 to 3, which is going to be from 1 to 3, which is more energy, which is the shortest wavelength. So we want to enter choice C. And that's it.